Let's take a slightly deeper look into inequality of functions. We would be doing a lot of plots and graphs of functions to explain, okay? So be a little bit attentive. The first case, okay? Let's take a simple linear equation. Y is equal to mx plus c. Basically, the function is mx plus c. Why do I say that this is a linear equation? Because the degree of this function is 1. It's a linear equation. Linear equations can be plotted as straight line. In fact, this line y is equal to mx plus c. I keep on saying it as a line. When you do coordinate geometry, you would know that this is a generalized equation of a straight line, which looks something like this, where m is the slope. If you do not know these terms as of now, nothing to worry about. I'm just explaining, you'll soon get to understand. And c is this length. It's called the y-intercept. It's easy to understand why it's the y-intercept, or why I'm saying that this is c. If you observe, this is the x-axis, this is the y-axis. The point where the straight line cuts the y-axis, there the value of x must be 0, right? This is the origin, 0, 0. And anything along this line, x is 0, right? So if you put x equals to 0, you get y equals to c. So that means the value of y at that point is c. So that point is 0, c, and hence it's known as the y-intercept. Very simple. Now, let's get back to inequality. I was talking more about straight line at that point. Observe, this straight line extends. It keeps on going. It's a straight line. It extends to infinity. On the other hand, it extends also to minus infinity. And within this graph, there are certain regions where the value of y is more than 0. And there are certain regions where the value of y is less than 0. Which are those regions? Anything above the x-axis is greater than 0. Y is greater than 0, or the function is greater than 0. Anything above the x-axis. On the other hand, anything below the x-axis, what is the value of y? Y is less than 0 over here. The function x is less than 0 over here, and y is greater than 0. If you get that image, if you understand this concept, you have understood half of inequalities, okay? And if you now look into this plot, this equation, y is equal to mx plus c, anything on this side, starting from this point, the value of the function is more than 0. Anything below it, the value of the function is less than 0. And what is this point? Do you understand? Do you recognize that this point, which let's say name as A, the dot with a circle, that point is the root of this equation? Do you recognize that? How? Because at this point, y is equal to 0. That means the function is equal to 0. Now, refer to my previous class. If you do y equals to 0, basically what you are doing is mx plus c equals to 0. What is that? That's the equality, solving the equation to find out the value of x for which the function is equal to 0. You are finding out the root. X equals to minus c by m. Actually, this point is minus c by m comma 0. When you find this out, you are basically finding out what is the root of this equation. So, the root is a very critical point. And anything right of the root, right side of the root, correct? Right side of the root means any value of x which lies right side of the root, the function is more than 0, greater than 0. I can say that this region towards the right is a plus zone and the region to the left is a minus zone. Just keep this picture in mind. It would be very important to understand the technique that I would explain soon that we use to solve inequalities for functions. I hope you get the importance of the root, okay? And visually this is clear. Now, this was only the first step. I have shown only a linear equation. Why don't we discuss the quadratic equation as well? Let's get to the case 2. Let's say I have a quadratic equation. Let me write down in a generalized form. Ax square plus bx plus c. Do you know how this looks? Or what is the plot of a quadratic equation? The plot of a quadratic equation is in the form of a parabola. Okay? It looks something like this. This is the parabola, and this equation actually, or this curve is representation of this quadratic equation, ax square plus bx plus c. Why? Or if you don't know this concept is discussed in the classes on how to draw plots of graphs, okay? You can remember it in this way. A linear equation is a straight line. A quadratic equation is a little bit curved compared to the linear equation. You can have a cubic equation as well. A cubic equation is more curved. As you go higher up in polynomials, the curve or the graph becomes more curved. Okay, there are more wiggles, we say. Anyway, now in this particular case that we have drawn over here for ax square plus bx plus c, even here, anything which is above the x-axis is positive for this particular function, and anything which is below is negative. So this region, the value of the function is negative, whereas in this region, the value of the function is greater than 0. Again, do you identify that there are 2 points like this? Let me name them as A and B. What are these points, A and B? Do you identify that these are the roots? Why? Because at A and B, these points A and B, the quadratic equation ax square plus bx plus c becomes equal to 0. If you know quadratic equations, how to solve, you know that these points, capital A and capital B, are nothing but the roots given by this equation. And criticality of the roots, observe. Once you cross the root, let's say the right side of capital B, this side, the function is plus, positive. After that, it's negative. The value of the function is negative. After that, again positive. So around the roots, there is a change in sign of the function. The function changes from positive to negative, and again from negative to positive. So the roots are critical. Okay. So do you think that for any function, any polynomial function or algebraic function, whenever we find a root, the function changes its sign from positive to negative or negative to positive just after a root? Well, it's true most of the times, but not always. Let me explain with the next scenario. Okay, I draw another curve of a quadratic equation. Let's see what happens over there. These are my x and y axis, and my quadratic equation curve, assume, looks something like this. What's the difference with the previous curve that I had drawn? In the previous case, the curve had crossed the x-axis at 2 points. Here, I have drawn it in such a way that it touches the x-axis at only 1 point. Is this possible? Actually, you have encountered these scenarios a number of times when you had solved quadratic equations, but maybe you never thought about it. You never thought about these curves. When a curve or when a polynomial, here a quadratic equation, touches the x-axis, just touches, doesn't cross at a particular point, it means that I have equal roots for that particular function at that point. Example, x minus 2 whole square or x square minus 4x plus 4, this function, it has equal roots, right? And what are those roots? What are those roots? Those roots are 2, 2, something like this, right? If this curve denotes x square minus 4x plus 4, then both 2 and 2 are roots at which are at same point. So this scenario that I have drawn over here, this is the scenario of equal roots. And if you have two distinct roots, two distinct real roots, you get this scenario where the curve crosses or cuts the x-axis at two different points, two different real values of x. Remember this term, real values. Why am I saying real values? You soon understand. Some of you might have already started thinking in the line of discriminant or this term b square minus 4ac, right? What is the significance of it? I would get back soon. I'd get back. Whoever has already started thinking in the line of b square minus 4ac, you are absolutely correct. I will discuss on b square minus 4ac after discussing another case. Let's get to the next case. The curve may be of a third type as well. Something like this. Here, the curve has not touched the x-axis at all. Can we have that scenario as well? Yes, we can. Now think about the b square minus 4ac. If b square minus 4ac is greater than 0, from quadratic equation, what do we know? We know that we have two distinct real roots. Case 1. If it is equal to 0, it must be the second case, right? We have equal roots, this red point. And if b square minus 4ac is less than 0, we don't have real roots. You know that, right? So you can say that we have imaginary roots. No real roots means the curve does not cross x-axis. Case 3. Okay. Now I have discussed enough of quadratic equation. Let's now get back to inequalities once again. There is some importance of the case 2. Observe about this root where we have two roots at same point, the curve has not changed its sign. On both sides, the value of the function is positive. There is no change in sign if you have two roots at the same point. This is very important. Again, remember this point. If you have equal roots at a particular point, there is no change in sign once we cross that root from right-hand side to left-hand side. Crossing means the value of x changes from the right-hand side to the left-hand side. There is no change in sign. Here, there was change in sign from positive to negative to positive. Okay? And this question doesn't arise in case 3. I discussed case 3 just for the continuation. Since I was discussing all these things, I decided to discuss on case 3. But there is one important thing in case 3 as well. Observe, this particular function is always positive. It is never less than 0. Keep this in mind. Keep this thing in mind. We may require this concept while solving some more difficult problems, okay? Now, quadratic equations, for quadratic equations, these parabolas or these curves, I have drawn 3 scenarios where the curves are all pointing upwards. This is not always true. There are scenarios where the curve points downwards. But even in those scenarios, these 3 cases remain. So for instance, I may have this kind of a scenario where this is the x-axis, the upper one is the y-axis. Here, what is the scenario? The curve has 2 real roots. I may have this scenario as well, and I may have this scenario. If you have understood the 3 cases above, you can identify the 3 scenarios here as well. Okay? This was all about quadratic equations, but most of the theory of inequalities or the concept of inequalities that would be required to get to that technique that I was talking about, all of them are discussed or are already identified in this scenario. Let me discuss higher order curves as well a little bit. Let's say a cubic curve. A cubic curve may look something like this. Okay? This is a typical cubic curve where you have more waves. The amount of waves have increased. And which are the roots here? This is one root, this is another root, and this is another root. And these are all distinct roots. There is no equal root case over here. So here the curve is positive. Here the curve is negative, positive, negative. Observe the sign keeps on changing. Okay. There can be another scenario where, let's say, the curve is somewhat like this. What does that mean? Here, there are two roots just touched, right? So two roots. Here there is one single root. So here it's positive, here it's negative, here it continues to be negative. Okay, I hope you are getting it now. Since there are two roots at this point, the sign of the function didn't change. Here, there is just one root. So the sign of the function changed from positive to negative. This is a typical cubic function case. We may also have a scenario or a particular cubic function which is like this. That means there is only one real root. The other crossing of x-axis doesn't happen. Here, this is blue curve that I drew. That's a different cubic function where there is only one real root. I hope you understand why I am saying that there is only one real root and not three roots. For higher order polynomials, you keep on getting such things. There is an important theorem called Descartes' theorem. It's not required, but if someone of you is interested, you can learn about it. It discusses on roots of polynomial functions. The number of positive roots, positive real roots, the number of negative real roots, and how to identify that for a higher order polynomial equation that's given by the Descartes theorem. We are not going into that because that's not required in this class. So whatever I have discussed so far are all based on the roots of polynomial equations and their representation on the graph. Let me continue a little bit more just through equation, okay? Let's say I have a polynomial equation, something like this, a generalized case. This is a generalized polynomial equation, and this would have some roots. What is the maximum number of real roots this function can have? N. But I used the term maximum number of roots. Why? Because there can be imaginary roots, there can be equal roots. The maximum number of roots that we can have is n, but it can have lower number as well. What's the easiest way to find out roots? The easiest way to find out roots is to factorize. You must have done factorization of polynomials in your junior classes, and those expertise would help you now. You have to factorize these polynomials to find out the roots. There is one theorem called factor theorem. If, let's say, x minus alpha is a factor of this polynomial, then f of alpha must be equal to 0. You can use that factor theorem to factorize this, and that is important. Why am I saying that factorization is important? If you are able to factorize this, let's say, into x minus alpha into some other polynomial function of lower order and equal to 0, you can see that alpha is a root. In order to solve inequality, you need to find out the roots, right? So factorization is important. And these roots help us to find out the intervals of positive sign, negative sign. I have done enough talking for today. This concept would help you now to connect with the technique that I would teach beginning the next class and the problems that we would be solving. Enough of theory done. We would now get into business while you'll be solving problems. First, we would understand a particular technique which we would be using while solving all algebraic kind of inequalities. Okay.